Alright, so the derivative of arcsecant. For the derivatives of the inverse trigonometric functions, you'll want to remember these. The derivative of arcsecant, and we'll say arcsecant of u, should be u prime over, or you can put a 1 on top and then multiply by u prime at the very end, but either way, there's nothing really other than a u prime like on top. But on the bottom there's an absolute value of u and the square root of u squared minus 1. And just for completeness, here are the others. Derivative of arcsine of u is u prime, and that's just, the u primes are always there because of the chain rule, over the square root of 1 minus u squared. And the last sort of important one, the derivative of arctangent of u is u prime over 1 plus u squared. Okay. But the one that we're interested in today is this one, although it may be a different one on the test, who's to say. So first of all, just remark that, it's not just arcsecant of x, it's arcsecant of 2x, but that's not going to be so much more complicated. All it means is that u is 2x, and then u prime will be 2. And then just shove that in here for u prime, and here for 2x. Absolute value of u, so 2x times the square root of, and of course you're going to want to do this in parentheses because you're taking the entirety of 2x and squaring it. So it's not like, it's not just 2x squared, it's 2x squared. Okay, but 2x squared minus 1, which you can simplify. It's going to be 2 over the absolute value of 2x times the square root of 4x squared. Right, if you take 2x and you square it, you get 4x squared minus 1, and that's all under the radical. And if you wanted to go even further, you could technically reason that the 2 inside of this absolute value can cancel out with this 2 that's up here. And you just end up with 1 over the square root of x times, 1 over the absolute value of x times the square root of 4x squared minus 1. Okay. And so any one of these would be acceptable, although ideally you would be able to tell what you would get if you squared 2x. But it's not like you gotta cancel this out or anything. Was there no integral? Yeah, there is. Okay, cool. That's the arctangent of u that we wrote down earlier. Okay. So this derivative is going to use a product rule because it is literally a product of two different functions of x. One of the factors is x squared, right? That's one function of x. The other factor is arctan of 3x, a completely different kind of function of x. So, let's see. Sure. Now the product rule goes, if you've forgotten, hopefully you haven't forgotten, if you take the derivative, say if you take the derivative of a times b, so let's just, it's a prime, that's saying you're taking the derivative, that equals a times b prime plus b times a prime. Just each one gets, its derivative taken and multiplied by the original of the other. So if we call x squared our a and arctan of 3x our b, we might want to find the derivatives of these so that we can construct this sort of a times b prime plus b times a prime kind of derivative. So a equals x squared, which means a prime is 2x. And on the other hand, if b is the arctan of 3x, well, that means that b prime, derivative of that, we'll follow this formula, but u is 3x and u prime is 3. So I'm just making a little remark of that, a little note of that here. So b prime is going to be 3 on top over 1 plus 3x all squared, or 3 over 1 plus 9x squared. It's impossible to see. There we go. Alright, so we should be able to mix a up with b prime and b up with a prime. So they just sort of go like, they get paired up sort of that way. So if the original function is h of x, then h prime of x should be a, which is x squared, times b prime, which is 3 over 1 plus 9x squared. Plus, okay, so this is a, and this is b prime, plus b, which is arctan of 3x, times a prime, and a prime is 2x. Simplifying that a bit, I guess you could multiply the x squared to the top of this sort of expression, 1 plus 9x squared, plus, I guess you could just switch the order that you're writing this in. So 2x arctan of 3x. But that's about it. There's no real reason to get it over in common denominator or anything. Yeah, the first 4 of these are going to go pretty quick. The integrals of the inverse trigonometric functions, on the other hand, they look similar in form to a lot of the derivatives, but there are tiny little differences. So the integral that becomes arctan is the integral, that's right, so if you have, let's say if you have 1 over 1 plus u squared down, 1 plus a squared plus u squared, or u squared plus a squared, it doesn't really matter, du, this equals 1 over a times the arctan of u over a plus c. And just here are the others. If you have 1 over u times the square root of u squared minus a squared du, that is 1 over a times the arcsecant of the absolute value of u over a plus c. And last, if you have 1 over the square root of a squared minus u squared du, that is simply arcsine of u over a, with no 1 over a in front. Okay, now of these, it looks like this is the one sort of that's being used here. Let me write this u squared plus a squared. Not like it really matters, but just to... Okay. So if a squared is 4, that means a is 2. If u squared is 9x squared, that means u is 3x. And that also means that du is 3 dx. So if you look at this, you can sort of tell that you don't have the 3 dx that you need for your du. You only have 1 dx. So one thing that you can do, and of course a different thing you can do is you can just divide by 3 and you'll have 1/3 du equals dx, and simply replace dx with 1/3 du. That's always something that you can do. But another thing that you can do is you can multiply a 3 on the inside and a 1/3 on the outside. Either way, you end up with a 1/3 on the outside that wasn't there before. So I'm just going to rewrite this, 9x squared plus 4 dx. And I'm just going to throw in a 3 and a 1/3 on the outside. So that I can write on the top 3 dx over 9x squared plus 4. Okay, so previously we reasoned that 9x squared was u squared. That 4 was a squared. And also that 3 dx was du. So making all those substitutions, it becomes simply du over u squared plus a squared, which perfectly fits the form of this arctan integral. So this should be 1 over a times the arctan of u over a plus c. And so a is 2. So 1 over 2 times the arctan of u is 3x over a, which is, again, 2. Plus c, and that is the indefinite integral. Now, once you get to this point, you don't actually have to rewrite it in this form and say that the integral is this. You can just skip right to writing, once you know what u and a are and that you have it in this form, you can just skip right to writing 1 over what a actually is times the arctan of what u actually is over what a actually is plus c. Yeah, what's up? Yeah, that's right, the 1/3 that was on the outside. Yeah. Don't forget about that. So it'll eventually be 1/6 arctan. Yeah, that's right. Okay. This is a similar integral, but it's not similar enough. This one actually has an x on top. And as for what that changes about the actual integration, it changes a lot. Specifically because it's no longer going to fit that in any of these forms, much less the one that we just used. This one has an x on top, not a 1. But what you might notice is that the bottom is quadratic. It's 9x squared plus 4, while the top is linear. What that means is that if you can say that u is 9x squared plus 4, well then du would simply be 18x dx. And you have that x right there. That's, that's notable. Maybe there's a way to make it into some other kind of integral. Okay. So similarly, to get du, you want 18x dx, but you only have x dx. So, of course you could divide both sides by 18 or something like that, but you could also just you could do this and say 1/18 du is at that x dx that you have. That is certainly a possibility. You could also just say you're going to multiply the inside by 18 and the outside by 1/18. But then what that gives you is u on the bottom and du on the top. Oh, I guess it's 18x dx. That's the... So that's simply 1/18 times the integral of du over u. Or if you'd like to write it a different way, 1 over u du. Whichever way, it's the same. Okay. But the integral of that is simply the natural log of the absolute value of u. Whenever you have something on the bottom with its own derivative on the top, that is a natural log. And u was simply this 9x squared plus 4, so just go ahead and replace that back after integrating. These are two equations, and their graphs, and the region in between them is highlighted. And you're meant to write a definite integral that represents the area of that highlighted region. So of these, the green line is definitely the linear equation, and the parabola is definitely the quadratic equation. So which one's on the top and which one's on the bottom is pretty clear. As for these points of intersection, maybe the axes won't be as clearly labeled on the test. So you'll want to know that to find these, you'll set the two equations equal to one another. So you're going to take x squared plus 2x plus 1 and set it equal to 2x plus 17. Since this is now a quadratic equation, get it to equal 0. Factor x squared minus 16 into x minus 4 and x plus 4, and set each factor equal to 0. To get your two x values. which in this case are -4 and +4. Which you could tell from the graph, but no guarantees that you would always be able to. Okay, so the integral is simply the integral from -4, and you can say x equals -4 if you'd like to be more specific about it, to x equals +4 of the top minus the bottom. And the top is simply the 2x minus 17. Minus the bottom, which is the x squared plus 2x plus 1. Dx. And you can simplify this if you want. Even this is fine. If you did simplify it, it would be, what, 2x minus 2x, so nothing. It would be -x squared, -17 minus 1. Right. That would be -x squared. Oh, this is should be a plus. Okay. 2x plus 17. Okay. There we go. So 16 minus 1. Yeah. So -x squared plus 16 dx. Either this or this would represent that area. So this right here is for the intersections or the bounds of integration. So this is a quarter circle in the first quadrant of radius 3. Has the equation y equals the square root of 9 minus x squared, or it also has the equation x equals the square root of 9 minus y squared. It's the same thing, just depending on what you're planning to do. And I would say that this would probably be the easiest with the disk method. But since you're rotating it around the y-axis, the disk method will necessitate that your slices be dy slices. It's going to be dy for the disk method. Dx. Oh. If you wanted to do a dx, you have to use a shell method, and that integration is a little harder. It requires some u substitution if you wanted to do the shell method. That's, if you really wanted to keep a dx, it would be possible. So because it's so if you want to do this with the disk method, and it's going to be easier despite the fact that it's going to be a dy integral. Because it's a dy integral, you'll want to use the representation of this curve that goes like x equals, whatever function of y. So the disk method would simply be pi times the integral from y equals, well, y appears to go from 0 up to a maximum y value of 3. So y appears to go from 0 to 3. And if you're taking these slices and you're rotating it around the y-axis to make these thin little disks, well, then the radius is simply this curve. The square root of 9 minus y squared. And that is the radius that is going to get squared as it gets put into the disk method sort of integral formula thing. And that's really good because that's going to cancel out with the square root that's there. So we're just going to have the integral of 9 minus y squared dy. And later, on Blackboard I'll post like how first of all, on Blackboard I'll post the actual review. If you wanted to print it out somewhere. But more than that, I'll post alternate methods for the next few problems. So if you really did want to see how it would be done with the shell method, if you were really insistent on keeping this whole process with respect to x, you'll be able to see that after I put that on Blackboard. But anyways, integrating this, it'll be pi times the integral of 9 is 9y, and the integral of y squared is y cubed over 3. And this is going to get evaluated from y equals 0 to y equals 3. So this is actually integrating. And so you're just going to plug in 3. And you're also going to plug in 0. Which in this case will be 0, right? If you plug in 0. But it's not always the case, and you don't want to. Yeah, you don't want to assume. You don't want to get something wrong just because you thought that every time you plug in 0, everything evaluates to 0. There are a lot of functions that don't evaluate to 0 when you plug in 0. Polynomials are not one of those, though. Polynomials with no constants, at least, which is sort of what always pops up with these integrals. Those do always evaluate to 0. I haven't put that on. Okay. So that's pi times 27 minus 9, because that's what? 27 divided by 3, which is, 18. Okay. Right, so this is just 18 pi. just check that real quick. 4. Two is, yeah, 18. Okay. So again, we're going to take this and rotate it around the y-axis. And I am actually going to recommend the shell method. The disk method is possible. You know, if you were to slice it like this, if you're really insistent on using the disk method. People tend to either be very insistent on using dx over dy, just because that's what they're more comfortable with, or either that or they'll be insistent on using disk/washer over shell, I guess because disk/washer is what they learned first or something, but you don't want to do this one shell. I mean, you can, and again, like, I'll post something on Blackboard that shows you what that would look like, but the whole thing is like, you know, you'd have to factor in like 2 different curves if you were talking about the height of the shell, and it's just also it would be dy. So if you have an opportunity to do an integral that is both dx and by height of the shell, I mean radius of the disk. You'd have to factor 2 different curves into the radius of the disk, or like the inner and outer radius of the washer. And that's, you know, I guess it's possible, but you'd also have to switch all the functions to being in terms of y. So it'd be a lot easier if you were just to do it using the shell method. So dx shells. So disk/washer is possible, but it would have to be dy. And that's because of that axis of rotation being vertical. Okay. So with the shell method, there are only 2 things you really have to think of. What is your radius function? And you'll notice that, the next one's the only other solid rotation, but in all these, the axis of rotation is just the x-axis or the y-axis. There's not going to be any weird, 3 minus x or x minus 3 on these. But you would at least have to remember that the radius for the shell method is, at the very least, just x. Because your radius starts out here, and your radius increases as x increases. It only makes sense the radius is literally x, as x goes from 0 to 1. The height of the shells, on the other hand, let me do that in a different color. Purple or something. The height of the shells, on the other hand, is determined by, well, all it's determined by is this function right here, this curve that's on top. The bottom curve is just y equals 0. The top curve is y equals the square root of x. So y equals the square root of x is the function that determines how high each shell is. And as for your bounds, this is a dx integral, so x goes from 0 to 1, so x equals 0 to x equals 1. Those are your bounds of integration. Putting all this stuff together, the shell method is going to be 2 pi times the integral from x equals 0 to x equals 1 of your radius function times your height function. Dx, that's it. So x times the square root of x, that is going to be x to the 3 halves. That's how you would incorporate the two together, because the square root of x is just x to the 1 half. X is just x to the 1. So if you were to multiply them together, you would just add the exponents. 1 plus 1 half, which is 3 halves. So that 3 halves is from x to the 1 times x to the 1 half, which is what is up here. Okay, so actually integrating that now, because you can. It's going to be 2 pi times, and you're going to take x to the 3 halves and use the power rule on it, so raise the power by 1. That's going to make x to the 5 halves, and then you're going to divide by 5 halves, or in other words, multiply by 2/5. So it's just 2 pi times 2/5 x to the 5 halves, evaluated from x equals 0 to x equals 1. Which, I mean, you can even combine these and say that's 4 pi over 5 times, just combine these coefficients together, times 1 to the 5 halves, and subtract whatever you get when you plug in 0, which is 0. But it won't always be. Eventually there'll be one that doesn't. And just 1 to any power is 1. So this just ends up being 4/5 pi cubic units of volume whenever you rotate this out. So the formula for the shell method is 2 pi times the integral from a to b of whatever your radius function is, which tends to just be your variable. The only reason it would ever be different is if you have an axis of rotation that's somewhere away from your x-axis or y-axis. And in that case, it would simply be a number minus your axis, or your number minus x or y or whatever, or x or y, depending on what your variable is, minus the value of that axis, times the height of the shells, which is just, whatever the top curve of each slice is, whatever the curve is that defines the tops of the slices, minus, if there is one, what curve defines the bottom of the slices. And I'll have all these up on the day of the test. If you're doing it in integral dy, it's just r of y and h of y instead. dy. So these are just two forms of the integral for the shell method. Obviously, you can't use the second one because of it. For this problem, if you're doing the integral dy, that's the disk method or the washer method. Okay, and this is the last of these volumes. Here you have the region bounded by y equals x squared, which is right here. It's this parabola. Y equals 0, it's here in red. And x equals 3, which is here in green. Okay. So for this one, you're going to want to, in two separate instances, rotate it about the x-axis and then rotate it around the y-axis. This region is easier to conceive of as, being sliced up this way. That is to say dx. Than it would be if you were to cut it this way, because then if you cut it this way, you'd have to talk about the slices, the tops of the slices being x equals 3, that vertical line, and the bottoms of the slices being, particularly if we were talking about it in terms of y, x equals the square root of y. And it gets, more complicated. But again, you'll see that later. Whenever I post, how the other ways of doing all these integrals on Blackboard later. So you'll just want to keep it dx, which means that around the x, when you're rotating it around the x-axis, that is going to be disk. So dx, disk. But then later, when you're rotating around the y-axis, the fact that those slices are still dx, which is preferable, is going to make that be the shell method when you rotate it around that vertical axis of rotation. So around the x-axis is going to be disk if you do it dx. But around the y-axis, it's going to be shell if you do it dx. So we'll just make a note of that right now. So around the x-axis, the disk method, that's going to be pi times the integral from a to b. So x appears to go from 0 to a maximum value of 3. So x appears to go from 0 to 3. Those are our bounds. And for the disk method, all we need is some sort of radius function squared, dx. And that radius function, the function that determines the radius of those individual disks as you rotate them out, that's just y equals x squared. So that's the integral. So this is simply x to the 4th dx, which integrates into x to the 5th over 5. And that gets evaluated from 0 to 3. And also there's a pi in front because it's the disk method. So this is pi times 3 to the 5th over 5 minus pi times 0 to the 5th over 5. That is simply 243/5 pi. Around the y-axis instead, that's going to be the shell method. So that integral is going to go 2 pi times, x still goes from 0 to 3. So it's going to be whatever the radius of the shells is, like these cylindrical shells. And that radius, in this case, is just going to be x for the shell method. Or just not actually write that because that would be confusing. But that radius is simply x. So r of x for shells, the radius is just x. And the height of each shell, if you look at these slices, the height of each shell is actually just the same as the radius for the disk method. It's still that x squared, that y equals x squared curve is what's going to be our height function when we're doing the shell method. Yeah, that's just 2 pi times the integral from 0 to 3 of x cubed dx, which is 2 pi times x to the 4th over 4. Or 1 pi times x to the 4th over 2 if you reduce this. And this is going to be evaluated from 0 to 3. so this is going to be pi times 3 to the 4th over 2 minus pi times 0 to the 4th over 2. So that's just 81 halves pi. So yeah, these aren't particularly complex integrals, but you do have to know what you're doing, I guess. But the integrals themselves are just x to the 4th, the integral of x cubed. And the last two problems are about arc length and surface area. Well, here we're given a function x, a function called x that is a function of y, and we're given bounds for y. So this is very likely going to be a dy integral. Let's just keep that in mind. The formula for arc length, dy, is the integral from c to d. I mean, you could say, little s if you need something to call the length. The integral from c to d, whatever your bounds for y are, of the square root of 1 plus, and if it's dy, it's going to be g prime of y squared dy. If it were in terms of x, it would simply be f prime of x being squared there, and the integral would be dx. Okay, so this is what we can call g of y. Okay, so g prime of y should be, just following the power rule first, take that 3 halves and put it in the front. 3 halves times 1/3, the 1/3 that's already there, y squared plus 2, and because of the power rule, after you take that 3 halves and put it in the front, you're going to decrease it by 1. So it becomes then a power of 1/2. And also, because of the chain rule, you're going to multiply at the end by 2y. Chain rule. Derivative with respect to y of y squared is 2y. So a lot of this stuff cancels out. The 3, the 3, the 2, the 2, and what you're actually left with is y. I don't know why I'm not writing this in green. What you're actually left with is simply y times y squared plus 2 to the 1/2, or y times the square root of y squared plus 2. You can actually write it however you want. So that's g prime of y. So g prime of y squared, if you just take that and you square it, And again, you can write it as a square root or as an exponent of 1/2 on a set of parentheses around y squared plus 2. It doesn't really matter. You'll be able to square it either way. But you get y squared, because that y is squared, and just a plain old y squared plus 2, because that squared gets rid of that square root that's right there. And if you distribute that y squared now, you get y to the 4th plus 2y squared. Okay, so you take this, and you just stick it right here. It is g prime of y squared after all, so you can take that y to the 4th plus 2y and just substitute it in for the entire g prime of y squared. That's right there. So what we're looking at is the integral from, well, it appears y equals 0 to y equals 2. Times the integral of 1, the square root of 1 plus y to the 4th plus 2y squared dy. And as usual with these arc length integrals, you want to be able to write this as being some kind of square, so that it cancels out with the square root. And you can do that if and it's easier to see if you reorder the terms. And we actually did something very similar to this, if not this exact same thing on Tuesday. Y to the 4th plus 2y squared plus 1. This is a perfect square trinomial. This is actually y. This is actually just y squared plus 1 all squared. And if you write it like that, you can cancel out the square with the square root, and you just have y squared plus 1. So this is simply just the integral of y squared plus 1 dy, evaluated from 0 to 2. That is y cubed over 3 plus y, evaluated from 0 to 2. If you plug in 2, you get 8/3 plus 2. If you plug in 0, you get 0 plus 0. 8/3 plus 2, 2 is 6/3, so 8/3 plus 6/3 is 14/3. So the length of this curve, whatever it looks like, you don't actually have to know what it looks like in order to be able to do it, is 14/3. It's 4.6, 4.7. Last, a surface area integral. The formula for surface area is, and it's going to be with a big S, or whatever letter you want to use, or maybe no letter at all, if you don't really even care about calling it a letter. This is going to be 2 pi times the integral from a to b of some radius function, and what your radius function is going to depend on what kind of axis you're rotating around. If you're rotating around a vertical axis, for example, you got some kind of shape like this. That radius is just x. if it's a horizontal radius, but you're still doing it dx, so you end up with something like this. Your radius right here, it's not x anymore, it's y. But you wouldn't call it y. You would call it whatever your f of x is. That's how you would describe the radius. Because the radius, no matter what kind of axis you're rotating around, the radius of something is always perpendicular to the axis you're rotating around. Okay. But it's, right, anyways, time to finish this up. It's r of x in front of the square root of the same 1 plus f prime of x all squared that you would have in a regular arc length integral. So if anything, it's sort of the same. This part is the same as an arc length integral. The new parts are this r of x that's in front and this 2 pi. That's the difference between a surface area integral and an arc length integral. But, just the same. Okay, around the y-axis, that's a vertical axis, so in fact, you can actually draw this out. You don't have to, though. Minus y equals, okay, so y equals x is 0, minus 1, okay. And it's a downward facing parabola with roots at 4 and negative 4. Yes. If they matter, yeah. So since x goes from 0 to 4, you're actually talking about this portion right here. So this doesn't actually matter, and this bottom part doesn't actually matter either. But you're taking this portion and you're rotating it around the y-axis. So I should probably add in a graph for this one. But you will be provided, like, the graphs for these solids and any areas you'd have to find.
What about the
yeah, the disc, the washer, the shell. Not the formulas for like what the derivatives of certain functions are, or like what the integrals of certain functions are, but yeah, formulas for things like volume or surface area or arc length. Yeah. Yeah, so you're taking this little curve and you're sort of rotating it around the y-axis, and it's going to form this sort of hollow bowl shape. It's not going to be filled because this is a surface. It's a two-dimensional surface. It's not a volume. But yeah, it's going to form this little bowl shape. So the radius, and because it's a vertical axis of rotation, the radius is just going to be x, just like it is here, because it's a vertical axis of rotation. Now, in order to tell what f prime of x all squared is, we'll start with f, which is 1 minus x squared over 16. take the derivative to find f prime. The derivative of 1 is nothing. The derivative of negative x squared over 16 is minus 2x over 16, which is just negative x over 8. And so f prime of x squared is x squared over 64. So the integral that we have is 2 pi times the integral from 0 to 4. X goes from 0 to 4, so x goes from 0 to x equals 4. Of radius function is just x times the square root of 1 plus this whole f prime of x all squared. That's just x squared over 64 dx. And that's actually a very easy integral because it is simply a u substitution with everything under the square root being u. U is 1 plus x squared over 64, which means that du is going to be 2x over 64, or, well, 2x over 64 dx, I should say. Or, simplifying that, x over 32. Or 1/32 x. We can also, yeah. We'll say 1/32 x dx. And, we almost have 1/32 x dx. We're just missing the 1/32. Okay, so 2 pi times the integral from 0 to 4 of, and I'm going to leave a little bit of space in front of the x, 1 plus x, but otherwise rewrite it pretty much exactly as it was. But I'm just going to deal with this by putting a 1/32 inside the integral and balancing it out with a 32 outside the integral. Okay, but that gives me, if this is u, that gives me the du that I need. (32 times 2 pi is 64 pi. So 64 pi times the integral of square root of u du. And technically speaking, my bounds are no longer 0 and 4. My bounds are, if I use this u substitution and I plug in 0, that's, 1? And if I plug in 4, that's 1 plus a fourth, so 5/4. So u technically goes from 1 to 5/4 right now. But you don't have to use them. That's just, I'm just saying that those are what the bounds are when you're talking in terms of u. Because the square root of u is really u to the 1/2, integrating that should give you u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. Let me move some things. Really should have been more judicious with my space here. Okay, so that gets evaluated from u equals 1 to u equals 5 halves. Alternatively, you could switch it back into terms of x. So that's 64 pi times 2/3 u, which is really 1 plus x squared over 64 to the 3 halves. And that would be evaluated from x equals 0 to x equals 1. I mean, it'd be the same numerical answer anyways. If you plug in 0 and 1 into there, that's where the 1 and the 5/4 comes from, so it's the same either way. It doesn't really matter.
I'm sorry, I missed step up. Why did you went from 0 to 4 to 1 to 5 or 4?
Oh, okay. So 0 to 4 are the bounds for x. X goes from 0 to 4, and that's just from here. Right. So in this u substitution that we use to integrate, u is 1 plus x squared over 64. So if you plug in the bounds for x, x equals 0 and x equals 4, well then you get u equals 1 plus 0 squared over 64, or just 1. And if you plug in 4, you get 1 plus 4 squared over 64, which is 1 plus 1/4 or 5/4. So if you want a bounds for u, they would be 1 and 5/4 based on the bounds for x being 0 and 1 and plugging them into this substitution. You don't have to have them. Like you can just say, oh, I don't actually know what these are. I'm just going to wait till I change it back in terms of x and then just use x equals 0 and x equals 1. But I just wanted something there. Yeah, like at no point do you have to find out your bounds for u. But do know that even if you change it back into terms of x, you're going to be plugging in 0 into 1 plus x squared over 64 and plugging in, yeah, sorry, this should have been 1. Or sorry, this shouldn't be 1, this should be 4. Yeah. But you're going to be plugging in 4 into there anyways. So, you're either plugging in 0 and 4 into the substitution early on, or you're going to be doing it at the very end, but you're going to be doing it either way. Yeah. Was that what you were asking about, or were you asking about that mistake I made with the 1 being the...
Oh, she was asking about 1.
Oh, okay. So that's what, 128 over 3 pi. So either way you do this, whether you're plugging in 1 and 5/4 into u or 0 and 4 into x here, you're going to end up with 128 over 3 pi times, I guess the simple way to do this would be like 5/4 to the 3 halves minus 1 to the 3 halves. And honestly, that's good enough. Well, if you really wanted, you could, I guess, evaluate a decimal approximation of that. 1 to the 3 halves is just going to be 1 anyway, so. Around 53.287, let's say. The only thing that's back here is a bonus question that's also going to be on the test. If you want to write it down, you can. But other than that, that's the review. Sorry, I wasn't able to make paper copies of them for y'all.
There's only 10 questions.
Yeah.